Good afternoon. So today we continue section 11.5, I think. Continued. So remember, we were dealing with alternating series, the ones that change sign, and it's easier for them to converge because sometimes we add terms and sometimes we subtract them. So we only did one example. Okay, we proved that this guy converges. Okay, so now let's consider some more sophisticated examples. So the next one is the following. Okay, so this series is alternating because of this factor, right? It changes sign at every step. So we apply the alternating series test. And there are two things that we need to prove, right? So first we have to prove that b n plus 1 1 second. So it was okay. So the first condition is b n plus 1 is less than b n, and the second is the limit of b n's is 0. Right. So here, let's not worry about the condition 1 at first. Consider condition 2 right away. What's the limit as n goes to infinity of 5n over 6n minus 4, right? So because bn here is given by 5n 6n minus 4. So we have to calculate this limit to satisfy the second condition. And this is very easy. We can divide by n. We always divide by the highest power of the numerator. We can see that this guy goes to 0. And the limiting number is 5 over 6. And that's not equal to 0. Okay, so we can see that this test doesn't hold. The test does not work. So does it converge or does it diverge? If the test doesn't work, then we cannot really conclude anything, because for it to work, we need both conditions to be satisfied. Okay, so we need more tests to assess the convergence of this particular series. So we are going to use the test for divergence. Remember, if the limit of an as n goes to infinity is not equal to 0, then for sure the thing is going to diverge. So we have to consider the limit as n goes to infinity of this whole expression, 5n over 6n minus 4. And we know that it's not equal to 0. In fact, it doesn't even exist. Therefore, the series diverge. Okay. So the fact that the test, the alternating series test, failed doesn't mean that it doesn't converge. It just means that we need more work. And in this case, the work is easy. We just look at the test for divergence. Question?
Yeah. I'm looking at the two conditions for the alternate series test.
Yes?
Is there a circumstance where the second one would be met, but the first one would not?
Yes, of course. This can go to 0. Let's draw Bn as a function of n. They can go to 0, but they can be like this, right? So the sequence goes to 0, so 2 is satisfied, but it's not a decaying sequence. You can see that sometimes it goes down, up, and so on. So for this particular setting, 2 is satisfied and 1 is not.
But in this situation, you take out the -1 term, which would cause that kind of popping, right?
So, okay, you're right. So we can envisage something like this. Okay. At 0. Okay. More questions? Okay. Another example. It forces us to test exactly this condition, the first condition. So let's look at the following alternating sequence: n squared, n cubed plus 1. Okay. So let's check 2 first. What's the limit as n goes to infinity of this sequence? So we can divide by n cubed, which is the highest power that we have. So we have 1 over n, 1 plus 1 over n cubed. And we see that it's 0. So 2 is satisfied. Now what we still have to check is condition 1. Need to check. Need to show that Bn plus 1 is less than Bn. How do we do this? So Bn is given by n squared, n cubed plus 1. Not immediately clear whether it decays or not. So, but it looks like a function. So we're going to look at the function f of n and take the derivative. So if it's a function of a continuous variable, well, actually, this is a little bit confusing. Let me replace the variable with x. Okay, f of x. To see whether this is decaying, let's take the derivative, df dx, right? This is the result of the differentiation, x cubed plus 1 squared. In order to calculate it, we have to differentiate a fraction. Right? So we have this thing in the denominator. For the function f to decay, this numerator has to be negative. Decays as long as 2 minus x cubed is negative, which holds if x is greater than cube root of 2. What is cube root of 2? It's some small number between 1 and 2. So if n is greater than 2, Bn sequence Bn decays. So this shows that we have both conditions 1 and 2 satisfied, and we can conclude that the series converges by the alternating series test. Questions? Okay. So let us go on to study alternating series. We start section 11 0.6. Okay? And we started from a definition. So a series AN is called absolutely convergent. If the series absolute value AN is convergent. And I clumped two definitions in one. It is conditionally convergent. If the series itself converges, but the series that consists of the absolute values diverges. So what are we talking about here? We could have, let's do an example, okay? Let's consider the series of -1 n 1 over n. Okay, we proved last time that this sequence converges. This series converges by the alternating series test. We applied it last time. By the alternating So the question is it absolutely convergent? Okay. Is it absolutely convergent? So to answer this question, we have to put an absolute value for each term AN. So we consider this. Okay. So whenever we have the absolute value sign, we can ignore -1 to the n. So this is the same as 1 over n. And of course, this is the harmonic series that diverges. Therefore, my original series is not absolutely convergent. Instead, it is conditionally convergent. So I can say that this guy is not absolutely convergent. It is conditionally convergent. Okay. How about the following example? If we look at this, okay, so consider the series of the absolute values. This becomes 1 over n cubed, and this is a p series with p equals 3, which is greater than 1. So this converges. Okay. So we can conclude that the given series, n cubed, is absolutely convergent. And there is a very convenient theorem that relates absolute convergence and conditional convergence. Okay. If a series AN is absolutely convergent, then for sure it is convergent. So basically, if we can prove that the absolute values converge, then the series itself has to converge. So let's consider an example which is a little bit different. So cos n squared. So first of all, you can see that the terms of this sequence do change sign. Some of them are going to be positive and some of them are going to be negative because we have a cosine and it takes various values, right, between -1 and 1. But we cannot say that this is an alternating series because for an alternating series, the sign has to change every step, plus to minus, or the other way. Here, we don't have that. Actually, the changes of sign are not as regular. Like the first term is positive, the next three are negative, the following three are positive, and so on. The sign changes in an irregular fashion. So it's not quite an alternating series, but it's a sequence whose terms do change sign. So it makes sense to talk about its absolute convergence. It makes sense to investigate that. So consider the sequence of absolute values. Okay, which is the same as cos n over n squared. Okay, so this is a positive sequence, and to prove its convergence, we can apply tests that are good for positive sequences. We notice that the absolute value of a cosine of anything at all is less or equal than 1. And that gives me a convenient inequality. So these terms for sure are less or equal to these terms. So what we have is a sequence with positive terms whose terms are always smaller than these. And we know a thing or two about this sequence, right? We know that this guy is a P series with P equals 2, so it converges. Therefore, we can say that this series with the absolute values, it's confined between 0 and the convergent series, so it also has to converge by the comparison test. By the comparison test, this guy converges, also converges, and therefore the original series absolutely converges. Cos n over n squared absolutely converges. In other words, what this says is that the absolute values of these terms converge, exactly like here. Now we apply the theorem. If a series absolutely converges, then it converges. So the conclusion here is that this guy converges. Okay. I'm sorry? Oh, okay. Sorry. So I write it here again. Converges. Okay. So how many tests did we apply here? We applied, first we applied the comparison test, okay? And we looked at the p-series. So we used the knowledge of the p-series. We concluded that the p-series converges. Then by comparison test, the absolute values converge. Therefore, the original sequence absolutely converges. And then we apply the theorem and say it converges. Okay, so there are several steps here, but they're all very easy. Fine. Next, we're going to have a couple more tests to check convergence, which are both very important. So the first one is called the ratio test. So this test has 3 parts. Okay. So when we apply the ratio test, as the name suggests, we look at the ratio of terms, okay, and we look at the limiting value of the next term divided by the previous term, the absolute sign, the absolute value. Okay, so this is the object that we consider for the ratio test. It's the ratio and the absolute value. And if this limit exists, and it's a number that is smaller than 1, then the series absolutely converges. And therefore it converges by that theorem. Okay. So what is the opposite of this case? So we can say that if the limit of this ratio is greater than 1, then the series diverges. And of course, there's a third case. Okay, what's the third case? Is equal to 1, exactly. A over AN is equal to 1. And in this case, the answer is we have no idea. It could be either way, right? Test the ratio test is inconclusive. And we'll have to apply further tests to say anything at all about convergence. So here's my first example. We're going to look at the series that looks like n to the 5 over 8 to the n. Okay? So this is a perfect candidate to apply this test, because each term looks like a ratio, and when we write down this expression, it will simplify. Okay, so this is the object that we always consider. So because we have an absolute value, I can completely ignore -1 to the n. So I'm not even going to worry about it. So an plus 1 is n plus 1 to the 5 over 8 to the n plus 1, divided by n to the 5, 8 to the n, right? So this is an plus 1, and this is 1 over an. Okay? So now we simplify in the following way. So we have 8 to the n, and we have 8. So I have 1 over 8. Okay? And I have n plus 1 over n to the same power. So this is a simplification. And the test requires me to look at the limit, the limiting behavior of this ratio. Let's do that. how do I calculate such a limit? I'm going to multiply and divide the numerator by n to the 5. Okay, so I have 1 over 8 okay. So as n goes to infinity, 1 over n tends to 0, and the limiting value is 1 over 8. So this is what I call L, capital, always in this test. And we have to compare that with 1. Because I have a strict inequality of the right kind, I can conclude that the series converge. Absolutely, actually. And converge. Okay. So in this case, the test works. What is my other example? So let me show you an example where we have this undecisive case. Yes, question?
When it says an plus 1, so it doesn't actually have to mean that it's like the next term. It's just some an, some...
It is the so we take what is an for this sequence? It's minus 1 to the n to the 5, a to the n. What is n plus 1? When we write down n plus 1, we replace n with n plus 1 everywhere. So it's minus 1 n plus 1. So here, instead of n, I just simply put n plus 1, and I have 8 n plus 1. For this test, all the minus 1s are ignored. Okay? So it is the next term with respect to an. Okay. More questions? Okay. So I want to show you when the test fails. Let's apply the test, the ratio test, to 1 over n. Okay, let's see what happens in this case. So we need an plus 1 over an. So let's do it step by step. What is an? That's 1 over n, right? An plus 1, we replace n with n plus 1. Is like this. So we have 1 over n plus 1 divided by an is like this. So the limit as n goes to infinity of an plus 1 over an is the limit of n plus 1. I can forget the absolute values because everything is positive here. And you can see that this is the same as this, and it's 1, unfortunately. So that's part 3 of my test. It fails. It does not tell me what happens. The test fails. But we know from before that this diverges, right? This is the harmonic series. But we know that this guy diverges. Next, I give you an example where the test fails, but the sequence converges. So let's consider 1 over n squared, right? So what is an plus 1 over an? We have n plus 1 squared over n squared. Okay? The same thing, but with squares. Now take the limit. again, it is 1. So I say that the test fails, but we know that this P series converges. Okay, so you can see that we applied the ratio test to 1 over n in 1 over n squared. The result was the same. The limit is 1. The limit is 1. So the test is blind in this case. It cannot distinguish between a diverging series and a converging series. So in this case, of course, in both cases, we have to apply other techniques. We've already done it. We already concluded that both of these can be evaluated. And this diverges, this converges. Okay. The last example of this, of the ratio test, is as follows. So let's consider the sequence n to the n factorial. By the way, when we have powers and factorials, the ratio test is good because things are going to cancel. Okay, so we consider an plus 1 over an. I'm going to drop the absolute values because everything is positive here. So what's n plus 1? We have n plus 1 to the n plus 1 factorial. Divided by an, so I have n to the n factorial. Okay. Now we want to simplify. So I'm going to split off n plus 1 from here. Okay, so this whole thing becomes this, right? Now I have n factorial, and n plus 1 factorial can be expressed as n plus 1 times n factorial. And finally, n to the n remains. Fine. So what can you cancel? I have n factorial, which is the same, and I have n plus 1. So what we have left is n plus 1 over n to the n, or 1 plus 1 over n to the n. Okay. So this is the sequence whose limit we have to evaluate. So let's write down limit as n goes to infinity of an plus 1 over an is the limit as n goes to infinity of this. Does anybody know what this is equal to? E, right? This is the famous number E. And in some courses, this is the definition of E. In some, it's a consequence. But this is a number that is between 3 and 4. So it's greater than 1. So you can see here, this is the case when the test works and it has a conclusive result. The sequence diverges. Okay, questions? Okay, very good. So one more test, which is almost like a twin brother of this. We're again going to look at 3 cases and compare the limit with 1. Okay, but the left-hand side looks slightly different. And I'll show you why we sometimes want to use this different version of the test. So the second test is called the root test. The root test. So again, 1, 2, and 3. So on the left, we have a limit as n goes to infinity of of a root of nth degree of the absolute value of an. Okay. Again, we call that L. And we compare this quantity with 1. So all the rest is the same. So if this is less than 1, then an is absolutely convergent. If this guy is greater than 1, then the series diverges. And finally, if this is equal to 1, this is the last case, the test is inconclusive. Okay? So very similar pattern that we observe here. Let us look at some specific examples. So again, yes, question?
Is there like an easy way to know why that works? Or
Yes, there's a proof. Let me see if I have time, and maybe I'll outline the proof. Okay, the rigorous proof is in the textbook. Okay, I'll say a few words. So let us look at one example, and then I'll explain why this works. We consider the following series: squared 2n cubed plus 10n, okay, to the power of n. So it is quite common that the series has the following term: some expression to the power of n. So an is the power of n. So this is your perfect candidate for the root test. Why? Because I will have to take an and extract the nth root. So the power n goes away, and it simplifies everything very much. So this is a perfect candidate. As soon as you see the power of n of the whole expression, that's your candidate for the root test. So we consider roots nth root of the absolute value. This is 5n cubed plus n squared, 2n cubed plus 10n. So this is the expression whose limit we have to calculate. So 5. So what do we do to calculate this limit? We divide by n cubed, right? These two terms decay to 0, and the answer is 2.5, which is greater than 1. So this is part 2 of the root test. The series diverges. Okay. So questions about this? So if we have terms that look like ratios, then it's good to apply the ratio test. If we have powers of n, not constant powers, but powers of n, we apply the root test. Okay, now a very good question is why this works, right? I want to talk about the ratio test because it's more intuitive. The ratio test compares the given sequence to a geometric sequence. So let me remind you, what is a geometric sequence? We have A, okay, AR squared, AR n minus 1 for the nth term, right? So what is A 2 to A1 for this sequence? Of course, it's AR over A. This is R, right? What is A3 over A2? AR2 over AR is R. What is AN plus 1 over AN? That's ARN, ARN minus 1. So that's R. Okay? So by the very definition, geometric sequence has term where each term differs from the previous one by a factor of R. Okay. Now, what do we know about the sequence, the series? This guy, n minus 1, converges if R is less than 1. Right? So this is the main thing that we have to remember about this sequence. And the reason for this is because the terms decay. They become smaller and smaller and smaller, and they become smaller fast enough such that it works. Question?
What does it say right below AR to n minus 1? Geometric sequence? At the end of the sequence.
Sequence.
Right there. Down.
It's the end.
And right, but I did it because you see the power is n minus 1, but it corresponds to the nth term, right? Okay, so this is what we know about this geometric sequence. Now let's go to the ratio test. What are we looking at? We are looking at the limit as n goes to infinity, a n plus 1 over a n, the absolute value, right? And we say that, let's suppose that this limit exists. So for some values of n, which are very, very, very large, the difference, the ratio between the next one and the previous one is going to be given by L, very close to it, right? It's the limit, but it's going to be very close to it. And now, if L is less than 1, then for very large n, this sequence is going to be similar to a geometric sequence whose difference between elements is given by L, and this factor is less than 1. So if this factor is less than 1, then the given sequence behaves similar to the geometric sequence. Oh, let's not even say that it's less than 1 or greater than 1. Let's suppose that the limit exists. Okay. In this case, the given sequence behaves similar to the geometric sequence with R given by L, right? So it's some number A, AL, AL squared, and so on. And now you can see very clearly that if L is less than 1, then the geometric sequence will converge. And therefore, the given sequence will converge. The sequence converges. And if L is greater than 1, the sequence diverges. Okay? So this test is based on comparing the given unknown, unexplored sequence to a geometric sequence and saying that when n is large, they behave similar. And then we apply the rule for the geometric sequence. What is interesting is that if we just have a geometric sequence, when r is equal to 1, then we for sure know that this guy diverges. It doesn't work for this test, because even though the given sequence can be very close to a geometric sequence with r equals 1, it's still not the same, and it may behave differently. That is the case that separates convergence and divergence, and then other further tests have to be applied to get the answer. More questions? Okay, I think that's it. Thank you very much.